Hello, in this video we are going to be looking at binary distillation, and I'm going to kind of work through the Chapter 4 Appendix A Lab 3 that is in your textbook. In the book it was done using Aspen, so I'm going to be recasting it for how you would do this same thing in CHEMCAD. So to start with, they have you select components. So if you click on select components, and we'll do this in the same way that we've done previously, but our components in this case are 1,2-dichloroethane and 1,12-trichloroethane. So, okay, if you just type dichloroethane, you'll see that there are two choices here. We want the 1,2. And trichloroethane, I want 1,12. Be sure you get the 1,12. Don't go for the plain up here because that'll be a mixture and will have incorrect properties. So I've added those two. We're just doing a binary system, so that's all I need. And say OK. And this will now make a recommendation for me on what I should be using as my thermo package. Now, in this case, it has a temperature range of 33.8 to 212, so near ambient to boiling, and ambient pressure up to 150 psi. And I'll just say, okay, I don't know for sure if that's wrong or right. I will just accept that. If I knew more information, then maybe I would want to change that. So, okay, I say okay. And it recommends UNIFAC with the latent enthalpy for the H's. That's okay. In the handout, they are recommending that we use the, Peng Robinson. Okay, so we can switch and do that. If you wish to stay with the other, you can. We don't have any data. In the book, all they say is that alpha is approximately constant at 2.24 if you read through the entire thing. I'm choosing Peng Robinson, going against their recommendation simply because the authors in their example made that as a suggestion. I will say OK and give it a moment. Okay, it looks like it's accepted that. I'm going to do my engineering units. The problem statement is all in SI, so I will go with the metric here. It's going to be in kilomoles if you wanted to do something else, but the problem statement is in kilomoles. They do have pressure given in, I believe, atmospheres. Yes. Okay. So I can switch that. Okay. Doesn't really make a lot of difference, but then apply. Now, if you read through this, it is going to suggest that you look at whether or not this is a good model. So to do that for a binary system, we are going to run our chart. So our TPXY. My components, I'll go with the di first and tri second. You can change the number of points if you wish, whatever. So I have what I want there. I'll say OK, and it will create these. And what you see is that this is a fairly ideal mixture, but they're fairly close boiling, so the bubble and dew point are not all that far apart. Okay, and this is the model that it comes up with. Now, if you want to check this, what they recommend you do is that you export the chart. Okay, export it to Excel as a CSV file. It's not fast. Okay, and this has all of my X and Y values here. And what they recommend that you do is that you check that the alpha is approximately constant at 2.24. That was the one data point they had. And so to do that, I need the K for dichloro, well, I'll just K for dichloro. And to do that, it's going to be Y divided by X. Okay, and then the K for the trichloro, well, it's Y for the trichloroethane, so it's 1 minus, that is not what I meant to type. Okay, here I should be, equals, parenthesis, 1 minus cell F6 divided by 1 minus the X value. So that's my Y and my X for the trichloro. And I can just copy that down. Okay, all right. So I have my K's for each of these. What they want is the alpha, and alpha is K, and they've specified that it is the dichloro divided by the trichloro, or compared to the trichloro. So alpha in this case is going to be KD divided by KT. And if we copy that down, okay, I did a very poor job of that. We see that the 2.24 is a little high. Is a little low rather. This is a little higher than that, but it is fairly constant. It actually, if you did the UNIFAC, what you would actually see is that it's closer to 2.4, but again, fairly constant throughout. So this isn't going to be a bad model. It's not perfect, but no model ever is. So that is a way of verifying our data. The next thing that they want you to do is to start your simulation. So to do a distillation, I'm going to need a feed. I'm going to have 2 products. And I need a distillation tower. So if you look through here, you're going to see a batch distillation. We will get to that later in the semester, not for a while. Going on down through, no. Way down near the bottom, we have shortcut distillation and SCDS distillation. Now, shortcut distillation is useful. It is going to be a way of doing the equivalent to McCabe-Thiele for multi-component systems to get a first guess. SCDS is going to be the rigorous calculations of material and energy balances. If you read that, let's see if I can get it to stay. This unit op is designed for rigorous multi-component distillation, including optional mass transfer and dynamics. So this is the tower that's going to get me the most detail, the most close to a true answer. And so that's the tower I want. So SCDS is going to be the one I ultimately always will wish. We will be using shortcut distillation, but again, not at this point in time. So I need to now connect all of my, okay, there's my feed, my distillate, my bottoms, okay? So I have my basic tower. I now need to enter my feed information. So this is my feed stream. The authors give us a pressure of 1 atmosphere. Okay. Vapor fraction. I'm trying to look at, saturated vapor feed. So vapor. And the flow is 100 kilomoles per hour, 60%. So 60 kilomoles of dichloroethane and 40 of trichloroethane. Okay, so I have my feed stream. Next, I'm going to go to my tower. All right, so this is where we want to enter all the information we have about the tower. I'm going to read to you what they say in the book. They want you to do an equilibrium style calculation. They're going to use numbering from top to the bottom, and they suggested using n equals 23. They're doing a total condenser, and the reboiler is a kettle, a partial reboiler, vapor liquid for valid phases, standard for convergence, and they have a distillate rate of 60 kilomoles per hour and a reflux rate of 2. Okay. Oh, reflux ratio of 2. Okay. So we have a condenser. This case it is a total condenser, so total or none is our best choice there. The number of stages is 23, and the feed stage is, oh, they did say that somewhere in there, and I didn't read that because, oh, it is stated in step 6. It is, we're feeding at stage 9, according to those. We have an equilibrium model. We are not doing reactive distillation. I don't know anything about the heat transfer, so I can't do that, and we are not going to have a 2 liquid phase system. If you have any of this information, typically it is recommended that you go with the top pressure that matches your input pressure. Okay. Normally, there would be pressure drop across, but if I only put this one pressure in, a single pressure, then it is going to assume that the pressure is constant throughout. That won't be a large error, but it won't be exactly right. In reality, you always have some pressure drop. Specifications is our next one that we need. Okay, so specifications. Condenser mode. Well, I don't actually have the condenser mode, but I do have, they said reflux ratio is R over D equal to 2. That was one of the things they gave me. So condenser mode, I have a lot of options. Just read through all of those, you know, when you get a chance. I can do any one of those. What they gave me is the reflux ratio. Okay, reflux over D. That would be L over D in our book. And then the reboiler mode. So I have a reboiler, so not no reboiler. That would be a mistake. You know, I can choose any of these things, but I don't know the reboiler. I have to enter. If I say click that I want there to be heat added, I have to tell it what that amount is. I don't know that. So if you go through these things, I don't know the boil up rate or ratio, but I do know the bottom mole flow rate. They told me that the distillate rate is 60 kilomoles per hour. They told me that the feed is 100. So therefore the bottom mole flow rate has to be 40, right? Okay, because I have to be able to input something out of each of these lists. Okay. I can add additional tray specifications. Yeah, so I can say something about a condenser. I can add side product information, etc. All right. And I think that I may be, yeah, done. Okay. I've entered all of the given information at this point. Again, I did not enter what they say is the distillate rate is 60 kilomoles per hour, because they said this requires me to put something in about the reboiler. Every once in a while you get something where it's like, I don't know any of this, and you have to make a guess, run the simulation, and then check the variable that they gave you. That does happen now and then. So, all right, I am ready. I've got this done. I can name these streams if I wish. So I will name this stream distillate, Well, I think I will. There we go. I can type. I will name this stream bottoms. Okay. And now then I'm going to run my simulation. All right. So it had no errors, it had no warnings. I can click on a stream and look at it to get more information, or I can get more information by looking at reports. Okay, that's, I can look at, say, the product streams. And if I do that, then I have here's mass flow rates. It has the molar flow rates. So I can, get the reports that I need to that way. I can also do it by clicking on individual streams. So those are your choices. Now, they're going to have you, kind of analyze your data and think about it a bit more. All right, so let's look at what's happening inside the tower, because it's done stage by stage calculations, so we should be able to look at those. So I'll do that by going to charts and choose column profiles. Okay, you can do lots of these different things at various points in time. We will not be doing dynamic modeling in this course, but it's something else that you can do. But if you look at the column profile and select, in this case, all units, it's the same as anything. We want it to select all the types of profiles. Kind of doesn't really matter. And say OK, and it will create graphs. So in this case, it's showing the temperature, and at the feed, it is going to be much warmer below the feed and much higher. Let's get that right. Much lower above the feed and much higher below the feed. Oh my goodness. Okay. Speaking is not my best skill right now. So I can look at that. I can also switch to other things if I want to. Let me come back to my chart, do the chart. This time, let's look at the liquid flows. Okay. And I just want to see how much dichloroethane is going from stage to stage. Okay. So this is the total amount of liquid, and this is how much this is the total amount of liquid, and this is how much dichloroethane is in each stage, okay, in kilomoles per hour. And so you can see the performance inside the tower using this. This is not done using McCabe-Thiele. That's an approximation. This is done doing the rigorous energy and material balances. Okay. Now, they recommend that you try several variations. For instance, they want you to get a distillate product that is 92 mole percent dichloroethane and a bottoms of 8% dichloroethane. That is not something that we were able to specify, okay, directly in our equipment there, but we can look at this and we can try things like, okay, what happens if I feed at stage 10 instead of stage 1, okay, and run this. Okay, if I look at these values, and you can play games basically that way and try different options. Excuse me, get back onto my graph. I can, engineering units, okay. I can choose at this point, like if I want to change that I would rather be in mole instead of mass for some of my output, right? They're giving me some of the stuff in mass. You can choose other things, but you can play with this, do lots and lots of calculations with very little effort, right? And that's the key. So we want to, see what would be the effect of, okay, I'm going to leave this feed at stage 9, but I'm going to add 2 stages, right? Run it, and then see what my outputs are, right? And so do this. You also, let me show you, there are some other things you can do in here. You can come into your specifications, and this is this box down here. Okay, when it finally gets there. I can change the reflux ratio. Okay, maybe 2 was too high. Maybe it would do better to do something lower. And I can also say that maybe at the condenser, I want, a variable, let's see, the component, mole fraction, in tray 0, no, I think I have to start with tray 1, okay, is equal to 0.92. And my component is 1,2-dichloroethane. Okay, and run that. So I can play lots of different things, different games here, and so that's going to make modifications to the way I'm operating this. Okay, if you over-specify things, CHEMCAD's going to make a choice and just drop some of your specs that you had, and so you need to make sure that you're going in and checking that, oh, is the reflux ratio still 2? Oh, you mean it changed it? Okay, good information to know. So what I want you to do is first start with drawing by hand. I gave you the paper, but you can also print it out from our chart. Let's see, no, this one right here. You can export this data and print this graph. You can also print from here, except for it keeps making my computer crash, so there seems to be something wrong with that. But you can use this graph and estimate, with a reflux ratio of 2, a feed that's saturated vapor, estimate how many stair steps you would need to achieve problem, problem A in this lab, okay? And use that as your starting guess. Now, what we're going to be doing next is we're going to start looking at multi-component systems. I'm not going to be able to do those using the simple McCabe-Thiele as a starting guess. So the first thing we'll have to do is come up with the estimate that's going to be our starting guess. When we get into our simulation, that's going to be our shortcut distillation. But then I have to ultimately do the rigorous combined mass and energy balances, okay? So we want to be very confident in what we're doing with a binary distillation tower, okay? So that then we will be able to do the more complex systems of multi-component or, second feed, any of those kinds of things we've been talking about in class. So that is the end of this video lesson. I do need you to actually do those problems that are in Appendix A. Okay, it's problems A, B, C, D, E. Try those. If you have questions, let me know, or you might chat with Dr. Tomasi. He is very open to you guys contacting him also. He is available pretty much 10 to 4 on Mondays and Wednesdays. And so I will see you guys back on campus. All right, bye-bye.